So Leibniz and Newton, as they were doing the limit definition of derivatives, realized that these patterns kept coming up. So they decided to turn these patterns into differentiation rules. So it's a way of going from the function to the derivative without having to do all of that limit stuff in between. So our first and most important rule, the one that gets overlooked the most, is if my function is a constant, meaning my function is just a number, then our derivative is going to be 0. And this is because derivatives are just a way of finding the gradient at specific points. Well, the gradient of a constant function, if we were to look at a graph, is just 0. There's no slope. It doesn't go up, doesn't go down. It's just a flat line. So because this is just a constant 0, our derivative, no matter where we are, is 0. So whenever you're asked to find the derivative of a constant function, you always write that f prime of x is equal to 0. That f prime of x is equal to 0. Now when we start throwing x's into the mix, then we have this, what's called the power rule. So this is known as the power rule of derivatives. This is one of your basic, most useful rules. So the power rule states that we take our exponent, we bring it down in front of our function, and then we take one away from our original exponent. So what this looks like, so this is f prime of x. Our exponent is going to become our coefficient. So we're going to have 3 times by x to the power of 3 minus 1. So that simplified down is 3x squared. If we do our next one, remember there's also Leibniz's notation, which we can write as dy dx is equal to, our exponent is going to become our coefficient, so we're going to have 10x to the power of 10 minus 1, which is equal to 10 to the power x to the power of 9. This is also a very important rule to remember. Remember that anything that doesn't have an exponent written has an invisible exponent of 1. So if I use my power rule here, I would say that f prime of x is equal to my exponent becomes my coefficient, and I would have x to the power of 1 minus 1, which could be written as x to the power of 0. But if you remember your rules of exponents, anything to the power of 0 is just 1. So the derivative of x is 1, meaning we always have a constant slope of 1. Sometimes there's already a coefficient out front. Well, that just means we have an extra set of multiplying that we have to do when we find our derivative. So this would be f prime of x is equal to, we keep our original 2, and then we just do our derivative steps that we did up here to the x squared. So we bring the 2 down, x to the power of 2 minus 1. So this would be 2 times 2 gives me 4x, and 2 minus 1 is 1, so you can write the 1 or not. So again, f prime of x, we keep the 7, take the derivative of 4, or x to the power of 4. So we get 4x to the power of 4 minus 1, which gives us 28x to the power of 3. Again, keep the negative 4 out front. Now we're going to have negative 3x to the power of negative 3 minus 1. So this is going to equal 12x. Negative 3 take away 1 to the negative 4. That also leads us into our examples when we have fractional polynomials. So these ones, we can see we have the exponent down here in the denominator. The easiest way to do this is to turn it into a form with a negative exponent. So you can use this rule here, but this rule can be a little confusing when we start throwing in other numbers. So instead, what we would do is we would change this into a negative exponent. So this is just x to the power of negative 3. Now I can just use that power rule. So f prime of x is equal to, bring that exponent down, x to the negative 3 minus 1. So that's negative 3x to the negative 4, which we can write back into this fractional form. The negative 3 stays up in the numerator, and we go x to now the power of positive 4. So you can see how this rule applies here. Our exponent became negative in the numerator, and we ended up adding 1 to the exponent this time. Another example. This time when I bring my exponent up, there's already a 4 there to begin with. So it's going to be 4x to the power of negative 4. So we do our power rule. So we're going to have the 4 stays there. Negative 4x to the power of negative 4 minus 1. Which is going to equal negative 16 x to the negative 5. Just going to be negative 16 over x to the 5. So again, you can see we just went negative our exponent times by what was already there to get negative 16, and then we added 1 to our exponent. The last example here, so this one we have our coefficient in the denominator. So that coefficient needs to stay in the denominator. So this is going to be written as 1/5 x to the negative 5. So when we take our derivative, f prime of x, we're going to have the 1/5 stays. Negative 5 becomes our coefficient. So negative 5 minus 1. So negative 5 times 1/5 is negative 1. So we're going to have negative x to the negative 6. So that's going to be negative 1 over x to the 6th. So you can see here, again, we still put the negative 5 on top. It just canceled with the 5 we already had in the denominator, just again, negative 1. So the last thing we do, because our polynomials usually aren't just monomials, meaning we just have one term, usually we have several terms. So when we have several terms, we just take the derivative of each term separately. So the first thing when I look at this equation that stands out to me is this guy. This guy tells me I should rewrite this equation so that I have it written as a negative exponent, which will make taking the derivative a lot easier. So I would rewrite this as f of x equals x squared minus 2x plus 6 minus x to the negative 1. So now that I no longer have that fraction, I can simply use the power rule on each of these individual components. So I'm going to have f prime of x is going to equal, so we're going to look at the first term here, which is x squared. So the derivative of x squared, we're going to bring the exponent to be my coefficient, and then we're going to take 1 away from the exponent. Then I look at my next term, which is negative 2x. So the negative 2 stays. And if we remember, the very important rule we should remember, the derivative of just x is 1. So the derivative of just x is 1. Then we look, I have a positive 6. Well, positive 6 is just a constant. When I take the derivative of a constant, it's just 0. So this is plus 0. And then our last term, negative x to the negative 1. So we're going to keep the negative. So this negative 1 is going to become our coefficient. So we're going to have negative 1 x to the negative 1 minus 1. So now that we have each individual derivative taken, we can just simplify this down into one cohesive derivative. So this is f prime of x. So this is going to be 2x minus 2. A negative and a negative gives me a positive, x to the negative 2. Which of course can also be written in that fractional form again. So that's going to be 2x minus 2 plus 1 over x squared. And that's all there is to taking derivatives.